So this is what happened in rocket propulsion. As you see, this system rocket is launched by some propelling of the fuel. This fuel was ejected and propelled and pushed the rocket going to in another direction. If you look into the definition of the third law of Newton's, or the action equal to reaction, the force that has been pulled it off or expelled it can be expelled, I think it's expelled, is equal to the force that pushing this rocket upward. So we will use this type of definition to explain. However, in the momentums, we already know that momentum equal to mv, right? And if there is some force exerted to the system, that means you have the change of the momentums with the time. This is the impulsive force due to the change of the momentums. Or you will see the impulse or the change of the momentums is equal to the force with the time difference. With definition, the change of the momentum this time is not only the velocity that changes, also the mass it changes as well, because you expel some gas out of the system, so there's some change of the mass and also change in velocity. That is why if you would like to find the differentiation of the momentums, that means you would like to find d between p that equal to mv. So you got the m dv and v dm as well. Since this v, you will know that is related to the expel velocities of the gas, which is how you eject the gas out of the rocket. Now we look into this detail of the rocket propulsion. There are three scenarios that happens. If you look carefully, initially the rocket is moving with the specific velocity, and this rocket has the mass of the rocket itself plus with the mass of gas. This is the gas that about to initially eject. Since the time passed, the rocket starts to eject some gas out. This gas has been rejected or eject out. It's been ejected so that the mass is get out and have some velocity of ejection. This is kind of like expel velocities. And this caused the change of the momentum to the system, since from the first state there's no gas eject out and velocity not change yet. We look after the relative information over here. Since we did learn about the relative velocity, VGE, that means V gas compared to the Earth, is equal to V of gas that eject from the rocket. This is velocity of gas relates to the rocket, and this one velocity of rocket that relates to Earth. This is the definition of the velocity in the figure of the relativities. So by this, you will have the definition of V gas that compared to the Earth, like V of gas that eject out. This is the expel part on this bit, and this is the velocity of the rocket compared to the Earth on this one. So now you have this information, and when the time changes, so from step 2 to step 3, that means not only the gas that initially eject out, it's also eject out with the time. So when the time change, the gas is getting out more. So you have some dm out. So that means your mass here is reduced. So you have the rocket that lighter, you have the gas that eject out more. This is also cause some change of the momentum as well. So now you have the velocity of gas compared to Earth from the initial moments. This is from the point 2 position, and this is when the time passed in the position 3, and the relative velocity of the gas is also look like this because you have some change of the velocity. This term is thinking like you eject some gas out, you have some change of the velocity so that your rocket have some increase of the speed for pointing out. And all these are the definition from the conservation of momentum. Momentum still conserved in this case if you look into this system as an isolated system. Both gas and rockets still in the same system. And you derive from this part and using the information of the relative velocity, and you can see the mass big M is from the rocket and the small m. Now you look only 2 and 3. In this case, this is from 2 even and this is from 3 even. So you derive all these parts to show the final step. This is what I would like to emphasize. If you are really interested into the early part, just feel free to derive it. But I just would like to emphasize on this part since we have short amount of time left before the quiz session. What is happened here? This is what is happened to state that the mass, which is the rocket, has some change of the momentums. This is the change of momentum of rocket. And the change of the momentums, I will summarize this again, of the gas that eject is equal. So the change of the gas that eject out equal to the change of the momentums of the rocket. That means the proportion has been effective this way. But the minus sign is due to the direction. The direction of gas ejection is going downward, and the direction that rocket moving toward is upward. So the minus sign is go over here. So if you do look after the delta as an infinitesimal, you will have dv. V here is the velocity equal to minus of v eject of the gas. This is the expel velocity of the gas divided by m, and you do some integration this term. So finally you will have the relation of the terminal velocities. This is the terminal velocity after you eject delta m mass. This v equal to v0 plus v ex ln m0 over m. I will explain this through the example. No worry about the mass and like this messy derivation part. If you would like to determine the thrust is kind of like a force that's exerted to the system. So you can see m dv by dt, this is ma, right? So the thrust that, you know, the mass of the rocket with the velocity change with the time equal to the expel velocities of the gas and the mass of the gas, the rate of the mass that's been ejected with the time. You will understand all these more through the example. This is how you get the definition. The definition is come from the way that rocket propel, right? And you know that the mass of the rocket with the velocity that change, the rocket has some change of the velocity due to the ejection of the gas. Since the gas has been ejected to the change of the mass of the total mass here, and you got some expel velocities. So this is how you have the initial information of the delta P rocket equal to delta P of the gas. This is also the part of the conservation of momentums. And you have some equality here. This is mean like you have m dv equal to minus vex dm, and by that you can derive to find this term, right? We will note that later. I would like to note this part. This is the velocities of gas that relative to the rocket. It's not relative to Earth, it's relative to rocket. And this is the velocity of rocket relative to Earth. Right? We did learn about some the relative velocities already, so you can determine whether it's relative to the rocket or relative to Earth. The definition is different. This is the terminal velocity, and this is the initial velocities when you relative the rocket to the Earth. Since the thrust is already stated, and this term is the rate that the gas was expelled, we can also with like a burn rate, how you consume the gas out. You will know that the mass is changed in terms of kilogram per second, or in a minute or in hour. You have to convert to have the kilogram per second as a SI unit for the final thrust determination. Now we take a close look to this example. I will try to wrap this up and finish this session, and then you will have a quiz afterwards. So now, this is what happened here. A rocket is moving in space and have the speed of 3 and multiply with 10 to the 3 meter per second. You would like to determine what? So the speed of the rocket that relative to Earth when the mass is reduced by half. That means initially you have the rocket that getting out from the Earth's surface and have the velocities of 10 to the 3 meter per second. And what happened? What happened next? The position afterward, this was eject the gas out, and the gas was ejected with the velocity of gas ejection of 5, 10 to 3 meter per second. You would like to determine from V0 here to Vf, which is this is cos delta V, right? Delta V. If you are Vf minus V zeros. And from the definition of this, since you know that the way that rocket have some propulsion, the change of mass that the gas of rocket ejects multiplied with the ejection velocity is equal to the mass of the rocket due to the change of its velocities. The direction is different, so you have the negative sign over here. So if you can remember the Lond equation, please remember it. But if you cannot remember it, you can derive it like this. Have m dv equal to minus vex dm. So you arrange this term, so you get dv equal to minus vex and 1 over m dm. So now you like to integrate this term from v0 to v and from 0 to m. From m0 to m, which is the m final. And here you integrate this term, you got v minus v0 equal to minus vex over, not over, with the integrate term of 1 over m, which is equal to ln like You integrate 1 over u du, you got ln u for the integration plus c, if it says so. So this term, if you do integration, you got ln m from m0 to m. You have the minus signs over here, so that means you have your Vex of ln, rather than you have the ln m minus with m0, you got ln m0 minus ln m. So this is how you got Vex ln m0 over m. This is your v minus v0. If you would like to determine the terminal velocity, which is in this case v equal to v0 plus Vex ln m, sorry, and this is not m0, this is just m, ln m0 over m. So you can just sub all the information in. If I cannot remember this equation, I will derive like this. But if you can remember it, you can write this equation and sub all the information in. So now the V0 is 3 10 to 3 plus we expel is 5 10 to 3, and ln m0s, you got initial m, and the final mass is reduced for a half, so it's m0 over 2. So this part you got ln 2, right, about 0.6, and this term you already know it. So you sub all the information, all the information in. Sorry if my tongue got twist now. So this is the final after calculation, 10 to 3 meter per second. You can use the relation, maybe just only the final line, to answer this problem. You can determine the terminal velocities of this propulsion system. For the B case, if we would like to determine the thrust on this rocket, and with the burn rate of 50 kilogram per second, how can you determine it? Again, the thrust is what you know, that the change of the gas, right, dm, and multiplied with V ejection is equal to the mass of the rocket with the velocity of this rocket chain. With definition, mdv equal to dmvex. Thrust is what the force that happened to this case. If you like to determine it, you just ignore the minus signs over here. So you can redefine the thrust or the force that exerts the system as mdv by dt equal to, just look only the magnitude of it, dm by dt multiplied with Vex. Because you would like to find the magnitude of it, don't care about the direction yet. If you would like to state the thrust that pushing the car up, the rocket upward, and you would like to see like how about this force, now you can put the vector signs in it. Or if you would like to know about the propelling force or thrust that exerted, you can have the minus signs on it. But in this case, we would like to determine only the magnitude. Since we know the burn fuel rate, so that means the dm by dt, we know the information here. And we expel is already stated the direction here. This is we expel. The fuel is eject in direction opposite to the rocket. So this is we expel. So now we know this information, so we can find the thrust. So the thrust is equal to dm by dt multiplied with Vx. So that is 50 kilogram per second already. So we don't need to change or do any conversion because we have the unit in SI unit here. and multiply with V expel, which is the velocity of this one is 5 multiplied with 10, 3, and finally you get the thrust equal to 2.5 10 to the 5 newtons. This is how you use the knowledge of the change of the momentum or the impulse that you did learn, and you know that in this conservation system, the impulse that gas was eject is equal to the impulse that rocket moving upward, and the mass also change, also the velocity also change as well. How about this one? This is another thing that state about the thrust when these firefighter guys hold the nozzle, try to using this water hose to like stop the fire here, right? You know, some force that you exert here is also equal to the force that exert here. This is the thrust that we known. Also, this system is another kind comparative to the rocket propulsion, because there's some change of the mass that you eject the water out. So in this case, you will have some water ejection and also force exert to the hose. So the water ejection means the change of the water and the velocity that water has been ejected out. So equal to the force that exerts to the hose means the mass of the hose with the change of the velocities. Right, you have the with the time, you have it with the time. This is the thrust or the force that you have evolved in this system. Since you know that the water discharge with this rate, 3,600 liter per minute, the density of water MOV is equal to 1 kilogram per liter. That means in this case, 3,600 liter per minute is 3,600 kilogram per minute. But you would like to change to second, so you divide by 60 seconds is 1 minute. So this is the conversion. You will know the rate of change of the water, or the rate of water discharging. So now, if I rewrite from what we know, so the thrust is equal to dm by dt multiplied with v ejection. That means you have the rate of change of the mass is 3,600 over 60 and multiply with v ejection, which is you would like to determine it, right? And the thrust here is 600 newtons. So you rearrange this term. Finally, you will get we expel or discharging speed of the water through the nozzle. This is the nozzle is 60 multiplied with 600 and you divide with 3,600. The final answer is 10 meter per second. This is how you use all the knowledge of the conservation of momentums, try to explain all phenomena that happen. You also learn about the central mass to represent the many particle system, and explain about the force and about the momentum that involved into that system. And all of these are the lecture in this session.